Well, we've had a little look at how basic telescopes work, but we need to have a look now at what their limitations are and why we bother to build huge, great telescopes when we could just use little ones. So we're going to describe and explain qualitatively two limitations of telescopes, and we're going to look at particularly whether these apply to reflecting telescopes or refracting telescopes. And then we're going to have a little look quantitatively at one problem which all telescopes suffer from. So the first one has got to do with the refractive index and wavelength. Again, if we remember back to Unit 2, we'll remember that when light goes through a prism, the light can be split into the colours. Why does this happen? Well, the refractive index of glass is different for the different colours. It's the change in speed that makes the light bend, so the more the speed changes, the more the light bends. So if we shine white light into a lens, whereas all the diagrams we've drawn so far just have the light coming down nicely to one point, what we actually get is the red light, the green light, the blue light going to slightly different points. So if we draw the beam in from the other side as well, then what we find we've got is different focal lengths for the different colours of the spectrum. So instead of having one focal point like the diagrams we've drawn before, we've actually got a range of focal points, so that makes it quite hard. If we were setting up a refracting telescope and we were making the separation of the lenses the sum of the focal lengths, well, what focal lengths are we talking about? We're talking about blue light or red light. The kind of effects this has in normal photography is this kind of effect. So here's a nice sharp image. What we start to get is these sort of blue and red tinges around the edges of things, which are here all the way through, but you can't really see them. But around the edge, you start to get this kind of slightly blurry image, and it's blurry because it can't be in focus for all the colours at the same time. You need to know the name of this. This is called chromatic aberration. Okay, aberration is a problem. Chromo is to do with colours. So this is a problem caused by different colours. And this only applies with refracting telescopes because this has got to do with the refractive index of the different wavelengths of light. If we were reflecting, it wouldn't matter. All the angles of incidence and angles of reflection would be the same. So this is only a problem for refracting telescopes. Okay, so that's problem number one. Okay, the second problem is what's called spherical aberration. When you make lenses and you prop them up by the edges, which of course you have to do so that the light can get through the middle, as you tilt that lens around, it'll start to bend out of shape. So a lens should be this shape, where these are parts of the surface of a sphere. The lens bends out of shape, so this is no longer a sphere. That's called spherical aberration, so a problem caused by not being a spherical shape. What happens is the light should go like this, so all the light coming through the different parts of the lens is meted at one point. What actually happens is this kind of thing. Again, you've got a blurry image here caused by the light not all meeting at one point. Now this is a problem for lenses and for mirrors, because if the mirror isn't the right shape, again, it won't all focus the light to one point. But the difference is with a mirror, you can put lots of support behind the mirror to keep it in shape, whereas with a lens, you can only really support it around the edges. If it's a glass lens, it's got to be quite thick and they get very heavy. And this is really the thing that limits the maximum size of a refracting telescope. Okay, so the problem that applies to both kinds of telescopes equally is the problem of resolution. If you think back to what you know about telescopes from the formulas we did before, we got this formula: the angular magnification is the focal length of the objective over the focal length of the eyepiece. It doesn't really seem to matter there how big the lenses are in a telescope, because this is just a ratio of lengths. Okay, you can make a small mirror with a very long focal length or a very short focal length, and therefore you can make any magnification you like. Okay, but what we run into is this problem of resolution. This might get us started to have a look at it. Okay, so what we see is here's some stars, just to remind us of the context. We're thinking about astronomy, but here's a car in the distance. Okay, or is it a car? Maybe it's a motorbike, maybe it's a cyclist, I don't know. It's only got one point of light. Why does it look like there's only one point of light? Well, because we can't resolve it. As it comes towards us, okay, at some point, what happens is that we can now see that there are actually two car headlights, so it was a car and not a motorbike. Okay, but we can't resolve those two separately. So when it's in the distance, okay, it could be two lights, it could be one light, they're too close together for us to see. Okay, here's a real photograph to try and illustrate that again. Here's a load of street lights. These lights on the motorway here are all double lights all the way into the distance. It's quite clear to see here that they're two separate lights, but when you start to look over here, you can't actually tell that anymore. If you could only see these lights in the distance, you might imagine those are single lights. Somewhere on the way up through this dip in the road, you must be able to start telling there's two. Okay, well that's what we're talking about when we talk about the angle of resolution. They're the same actual distance apart, the two lights, but they make a bigger angle with the eye because they're closer to us. And what we need to say is, well, okay, how far away is it that we can see these two as two separate lights? When do they just become one indistinguishable source of light? Okay, so what we need to understand is that when we look at a light, it doesn't actually look like a single light when it hits the back of our eye or the whatever detecting mechanism we're using for a telescope. Okay, we get what's called an airy disc. This is the diffraction pattern as the light comes through our eye. So there might be a tiny, tiny speck of light in there, but once it's come through our lens of our eye, through our pupil, and been diffracted, then actually what we get on our retina is a pattern like this and a pattern like this. Okay, it's quite clear here there would be two stars in this image, but the question is, how close do those stars have to get before we can't tell anymore that that's two separate stars? Let's have a look at this animation. Okay, so on this one, again, scale's always a bit of a nightmare in astronomy when you try and draw a picture, but here's two stars. They're 100 astronomical units apart and then 9 light years away from us. This is what we expect them to look like. So if we have a huge, great telescope with a 10-meter mirror, this is what we'll actually see. Okay, don't worry about the numbers too much on here, okay, but we're just trying to make the point of how it works, that as we try to look at those with a smaller and smaller telescope, okay, what happens is we start to see more and more diffraction. So the airy discs of these two are getting bigger and bigger, but you could still see there were two stars, okay, but as they get to this kind of stage, somewhere around here, we're going to struggle to see now that that's two stars anymore. Maybe you can just about see that's two stars, but pretty soon after that, I think that's probably just going to look like one star. Okay, so the bigger the mirror we get, the better our angular resolution, the more able we are to separate objects with the same angular separation. So just to try and illustrate that in a slightly different way, this is the light that you see from a single source of light down the middle here. This is what actually gets through onto your detector. Okay, how much this spread is depends on the size of the aperture that it's going through. Remember, the smaller the aperture, the closer it is to the wavelength of the radiation you're looking at, the wider the diffraction pattern will be. Okay, so we've got two stars up here. What we start to see is the diffraction pattern from this star here, the diffraction pattern from this star here. Of course, we can't tell that this light's come from two different stars, so what we really see is the total of those two. If the total looks like this, it's quite clear that there's a darker bit in the middle, and that's going to be resolvable as two stars. This is just about at the limit when you can just about tell us the dip. Okay, and then this is clearly, you're not going to know that that light's come from two different stars. This is just going to look like a single star. Okay, this is the sum of these two comes up to here. And the Rayleigh Criterion, this is the criterion for being able to tell if you'll resolve it or not, is when the peak of this one corresponds for the first minimum of the other one. So if you remember back to our objectives, we were trying to look at a quantitative look at this. Well, the quantitative rule is that the smallest angle you can resolve is the wavelength that you're looking at divided by the size of the aperture. Sometimes you'll see an extra number in here according to whether we're looking at spherical apertures and things, but that's the one that's on the spec. That's good enough for us. Okay, it's an approximation anyway, so we're not going to get too worried if there's a number like 1.2 in here or something. Okay, it's just to give us a reasonably good idea. So if the angle that two things are actually at is less than this, then we're not going to be able to see that they're two separate objects. Just a couple of things to think about for this. So the first thing is, this is why you need a big mirror in your telescope or a big lens. So you make the lens as big as possible. This is an 8-meter reflecting telescope in Japan, a Subaru telescope. But also, just as importantly, what about if we're not looking in the visible? What about if we're looking at, for example, radio waves? Lambda becomes very big, If lambda becomes very big, your smallest angle of resolution is going to become very big as well, so you're going to run into big problems unless you make b nice and big. So if you're going to look at, for example, radio telescopes, then you need a very big telescope to do that.